Morning. I am Kaustubh Datto. Today I am going to give a brief lecture on introduction to the distribution function. Today's topic based on introduction, probability on of an event, random variables, probability mass function and probability distribution function, mean and variance. In probability theory, we look at all outcomes of a statistical experiment and assume that they constitute a set S. We call it sample space. The elements of S are called the sample points. Suppose, for example, the simple statistical experiment is conducting and suppose we are tossing one coin. The possible outcomes are head and tail. So whenever we are tossing a coin, the corresponding sample space will consist of two outcomes, head or tail. Similarly, if two coins be tossed simultaneously, in that case, each outcome of tossing one coin can be combined with the outcomes of tossing the other coin. So, required sample space will be head head, head tail head, and tail tail. An event is a subset of a sample space. In many problems of probability, we are interested in events that are actually combinations of two or more events formed by taking unions, intersections, or complements. Probability of an event is a set function satisfying the following axioms. The probability of an event is a non-negative real number, that is probability of A always greater than equal to 0 for any subset A of S. Next, probability of the whole sample space is always 1, and if A1, A2 is a finite or infinite sequence of mutually exclusive events from S, then probability of their union is equal to sum of their individual probabilities. Here one thing I want to mention, if A and B are two events such that A intersection B is equal to phi, then A and B are said to be mutually exclusive. Another interesting notion in probability theory is random variable. Sometimes we cannot assign the probability to each of the sample points. Rather, we are interested about one macroscopic property of the whole sample space. We give the formal definitions of random variable in that way. Suppose S is a sample space with a probability measure and x is a real valued function defined over the elements of S, then x is called a random variable. Collection of all the values of the random variable x from S to R is called the range of the random variable, and it is denoted by R of x. Depending on the nature of Rx, we generally define or classify two major types of random variable. One is called discrete random variable, another is called continuous random variable. If Rx is finite or countably infinite discrete point sets in R, then the corresponding random variable is called discrete random variable. Whereas Rx is some interval or the countable union, intersection or complement of some interval, then X is called continuous random variable. Next, we try to define a function from the range of random variable to the real number subset 0 1, close 0 1, in such a manner that will satisfy certain properties, or rather it is consistent with the axioms of probability. That type of function individually gives us the notion of the probability of the whole sample space. If it is defined on discrete random variable sets, then it is called probability mass function. If it is defined on the continuous random variable, then it is called probability density function. Suppose x is a discrete random variable, a function defined on Rx can serve as the probability distribution of a discrete random variable x if and only its values fx satisfy the conditions fx greater equal to 0 for all values in Rx and summation of fx equal to 1, where the summation extends over all the values within Rx. Similarly, if x is continuous random variable, a function defined on R can serve as the probability density function of the continuous random variable x if it satisfies the conditions summation fx. Instead of summation fx, we take the integration fx greater equal to 0 for all values in R and integration minus infinity to infinity ft dt has to be 1. Next, we define mean and variance of a random variable. Expectation or mean of a random variable x is defined as follows. X is a discrete random variable and if x is the PMF of x, then expected value of x is defined to be summation x of x. Definitely that sum runs over all x belongs to range of x. Correspondingly, if x is continuous random variable and if x is the PDF of x, then the expected value of x is integration x of x dx. Integration runs over the all range of random variable. Instead of x, if we take some weight function gx, expectation gx is defined to be summation gx of x or integration gx of x. Using the above definition, we will clearly define variance of x and it is defined as expectation x minus mu whole square. That means if x is a discrete random variable, variance of x will be summation x minus mu whole square into fx, and for continuous case it will be x minus mu whole square into fx dx. We denote variance of x by sigma square, where sigma, the positive square root of variance, is called the standard deviation. Thank you.